So we have the common ion effect. When we have that, we can use the Henderson-Hasselbalch equation. It's always going to depend on the fact that you're working with an acid and its conjugate base. So when you're looking at these concentrations, you're going to be looking for a concentration of an acid and a concentration of its conjugate base. Then you'll be able to figure out the pH. When the concentration of the conjugate base is exactly equal to that of the acid, you've got the fraction is just 1 and the logarithm of 1 is 0, so the pH is exactly equal to the pKa. We will do something a little later that shows the derivation of that and why this actually works, but right now we're just going over what's going on. Now, if there is more conjugate base than there is acid, the fraction will be greater than 1, the logarithmic term will be greater than 0, and the pH will be bigger than the pKa. So you can see that if you continue to add more conjugate base, you're going to be forcing the amount of hydrogen to be less. This follows along with Le Chatelier's principle. And since the amount of the hydrogen is less, your pH is going to end up getting bigger. And the opposite direction of the same is true. If the base, the concentration of the conjugate base is less than the acid, then the fraction here will be less than 1, and the logarithmic term will be less than 0, and the pH will be lower than the pKa. You can also use it if you're trying to do the pH of a weak base with its conjugate acid. Oh, okay. As usual though, if you're working with something that was developed for an acid and you're trying to use it on a base, you're going to have an extra step. Fortunately, when you're talking about the pKa and the pKb, you can get one from the other by recognizing that the two of them together have to add to 14. So wonderful. That's not so bad. We just have to recognize what we're doing and do it. And we have a problem here. Number *3. It says calculate the pH. And they tell you that it's going to have methylamine. So the concentration of the methylamine is 0.25 molar. And the concentration of the methylamine hydrochloride, oh, that's a strange name, but what is the actual formula of that? It's CH3, NH3, Cl. But this comes apart ionically, so I don't have to worry about the Cl. And I can say that that is 0.75 molar. I said it came apart ionically, so I better put a positive charge on there. So I can look at this and say, oh, here is the base, and here is its conjugate acid, because you can see that we have an extra H and a positive sign. So this is now the base and its conjugate acid. They've given me the K sub B, and they've given me the pKb. Well, let me work with that pKb. I want to use pKa because of the fact that I'm going to use the Henderson-Hasselbalch equation. So if the pKb is 3.36, then the pKa is going to be 14 minus that 3.36. I'm going to get 10.64 for the pKa. All right, which is the first thing that I need to put into my Henderson-Hasselbalch equation. My pH will be my pKa, 10.64, and then I am supposed to add the logarithm of the base over the acid. Well, that's the base. That's the acid. Okay, so the 0.25 over the 0.75. So that will be 10.64 minus 0.48. And I will get that the pH is 10.16. So it is not as basic as it used to be because there's more conjugate acid in there than there was base. That makes sense. If there's more conjugate acid, I'm going to expect it to be more acidic than it started out as. So it makes sense.